Okay, let me start the sessions. And the sessions today, I'm going to introduce to you integral. Okay, hopefully, I think, okay, there are some more to come in. Okay, okay, there are some more to come in. Doesn't matter, but we just start slowly. Okay, today I'm going to introduce to you a topic, and it's another important topic. And before that, tomorrow I'll start with you the lecture as well. Okay, I will take over from Dr. Low, and I'll start the lecture. And tomorrow's session will be a PDF. Okay, that means it's a partial differential concepts. I will introduce to you partial differential concepts, and but anyway, the sessions will go parallel. Okay, the session will go parallel, and that means what I mean by parallel. I will continue the tutorial, and you can see the lecture also will go on for the 4 weeks. The coming 4 weeks, I will take over from Dr. Low. And the integral in this case, we will see my sessions. I didn't start with the function. Some of you might be a bit curious to why am I started with the integral and differentiation in the first session. Okay, because as you all have seen, you can see that integral and differentiation playing very important role. It's a fundamental understanding because if you wanted to explore further into the limits, or you wanted to explore further into the functions, you need this integration and differentiation. Therefore, I strongly recommend, and I strongly request all of you to really master the skill of integration and differentiation. Okay, without wasting any more, okay, the time is already 11:07. Okay, let me start with the simple simple sessions with you. And okay, the first thing I would like to ask you, what is dimension? Okay, okay, simple. You can respond to my question. Okay, what is dimension? When we say dimension, because day to day we are dealing with the dimensions, right? New dimension, new. Always we used to this kind of words. Okay, when in the communication we use that word dimension. Drawing staff. Okay, thank you. Engineering drawing staff. Some more? Anybody else? Okay, some of them are joining still. Okay, left the meeting. Anyone else? Oh, okay, measurement. Okay, good. Some more. Okay, some of you say that this is when we say dimension. Okay, why am I started with the word dimension here? Okay, it's a very important, because it's very important to learn integral. Before we move into the integral, we need to know dimension. If we some more, any other feedback? View, set of value given to each side of an object. Okay, it is okay, good. Some of you giving some feedback. That's very nice to hear from you. Some more? Okay. Okay, joining the meeting. Okay. Now, in simple, I may say dimension is okay. Please follow today, because today's lesson is something very interesting. Before I introduce the integral in detail, I want all of you to have some basic understanding. Okay, the basic understanding of the universe and the space. Okay, let me start with the simple logics here. Okay, dimension can be explained as a kind of sorry. Wait. Say, come. Sorry. Okay. Wait. This is the problem with the okay. Dimension basically can be explained as something called a constituent. Okay, it's a constituent. It's a constituent structure. Okay, it's a constituent structure of all spaces, all the spaces, and its position in the time, okay. Two things. It's a kind of constituent structure. Okay, dimension basically is a structure that we can analyze in of basically we can see only one space, but I put here the word called all spaces. Do we have many spaces? That is a very interesting question, and those really can follow. Those are following like cosmologists or what you call advanced physics or particle physics. They will realize. They will agree with me. There are not one space in the space. Basically, there are more than one space. Okay, that's what I'm going to discuss today. Okay, constituent structure of all spaces and its position in time. We're going to analyze the time as well, but I already mentioned to you in the previous sessions, okay, for the what we call differentiation. Basically, time is invisible. All of you will agree with me because time is invisible. Therefore, how do we measure the time? Basically, the measurement of the time can be only measured based on the quantum of events. That events can be as small as possible, but I said that word called quantum. Quantum means is the minimum that possible, minimum possible state of events. Okay, therefore this is what we say infinitesimally smallest time. Okay, we are talking about the infinitesimally smallest time. Now the second question that I want all of you give a try. Okay, in this okay, I'll take this copy. I'll go to this. Okay, now oh, what happened? How many dimensions that we can observe in the reality? How many? Can you give us suggestions? How many dimensions? Maybe it's not more than one. It could be more than one. How many dimensions? Okay. Some of you say 3D. Yes. Some put 5. Some 4. Some say 4. Some of you say 6. Some saying okay. Okay. Various answers. Okay, some say 6, some say 3. Very interesting. But if I face to face, I will able to demonstrate to you what is this. Okay. Anyway, many of you say 3, and some of you say 4. May I know what is that? Okay, let's say. Okay, basically, many of you will agree with me. There are 3 dimensions. Okay, what are they? If in a simple sense, some of you may agree with me. I can see this 3. Okay, I can see this 3, and this is what we call as a Z. Okay, that means it's a height. Okay, width and length. Okay, basic. Wait. Okay. I say Y. Okay. In this case, this is all of you will agree with me. There are minimum that I can see, obvious, in reality that I can realize 3. But some of you say 4, some of you say 6. How could you, go more than 1? Can you suggest to me what is the additional dimension that I can go for? Can you give me the, very good, K. Jiang Yang. Okay, you say time, and Kevin Raj, time, very good. Some more? Okay, okay, that means some of you say there is another one more dimension to follow. Some of you just say there is another dimension to follow. Okay, I will say this is a 3D. You can imagine this is a 3D, and another one more dimension that you already introduced to me, that is time. That is very interesting. Okay, with this 3D, you are moving into this. We are adding one more. Could you, some of you, okay, please unmute your audio. Okay, you can see that from 3D, you can move into the another state we call, okay, 3D, we add one, okay, one more dimension here called time. Therefore, it's become 4D, okay. Now, almost all of you will agree with me there are 4D. But what about, is there any more dimension? Some of you say 6. Can you add? Do you able to add into reality? The question is in reality, huh? In reality, can we can observe in the reality? Okay. Yeah. Oh, Kevin. Okay. Some say 12D, some say 11D. Beautiful. Okay. Beautiful. Yes. Yeah. In string theory, okay, when we follow string theory, those are following string theory, definitely they will agree. You can go up to 11, and after that you can extend to 12, 13, and etc. But minimum you need to. We can go up to till today. They already proven there are 11 dimensions. Okay, 11 dimension in string theory. Okay, according to the string theory, there are 11 dimension. Okay, beautiful. But anyway, this is time plus 3D. Okay, this is the general relativity theory. Okay, according to the general relativity theory and special relativity theory, we will follow 4 dimensions. Okay, and this dimension actually is the greatest. You may think this is a contribution from the Einstein. Okay, of course, yeah, almost all of you will agree, sir. Yes, of course, this is a Einstein contribution, but there is another guy behind the scene, and he is the real contributor for this 4D. Okay, and his name is, anybody know? Anybody know? Beside Einstein, Minkowski. Wow, very good. Okay. Oh, beautiful. Oh, beautiful. Okay. I think this year, I think many of you are so very interesting. Okay. Last year I did ask many, none of them answered this kind of question. But okay. Okay, beautiful. Okay, Minkowski. There are this is a 4 dimension. Basically, is actually is a contribution from Minkowski's, but Einstein actually used his idea and extend the logics to the general relativity theory. Okay, beautiful. Okay, what? Okay, how do the integration related to what we are studying now? Okay, that's what I wanted to introduce to you. Okay, now, and next question that I want you all to answer. Okay, we go for the simple question here. Integration. Okay, what is integral? Okay, then I'm going to connect this. Oh, okay, let me finish this part. Okay, I haven't complete this part yet. Okay, some of you may be a little bit curious, how can the time can be in the 3D? Okay, in the 3D features, when any object, when you see the object is moving in the 3D, then automatically time will be incorporated. Okay, time will be incorporated. It means anything, when you start walking on the floor or any corridor, then automatically you are in a 4D. Okay, you are automatically in 4D. Basically, you can see there is a height, there is a what you call width and length. Then immediately you can identify you are moving away, from one place to the another. That means you are incorporating another dimension called time inside. Okay, that's what we call 4D. That's why almost all of you will agree by now. Okay, we no need to go for the string theory and to explain further about fifth D and sixth D, but mathematics allow you to understand fifth D and sixth D and etc. Okay, and etc. Basically because it's possible. Okay, in mathematics, only in mathematics world you can see extra dimension easily, very comfortably. I can demonstrate to you from 4D how to move into the fifth D. Okay, but today's lesson is not nothing, basically is connected, not to say connected, but I do want to connect that now at this moment. But anyway, the most important things for you to at this moment to master is at least you should know there are 4D in our reality. Okay, then the mathematical world allow you to go to the 5D, 6D and etc. Then that in some other sessions, maybe when I use a face-to-face class, that I demonstrate to you. I want to demonstrate. Instead, I don't want to show you through this kind of pictures, which is not that interesting. Okay, now get back to this question. What is integral? What is integral? Any answer? Okay. Okay, integral, basically I'm going to under area under a curve. Very good, very good, correct. Okay, the basic answer is correct. Area under these things, what you call under a curve. Okay, now this is what you've been taught. Today I'm going to introduce to you something in a different way. Okay, without wasting further time, then I want okay, first let me put it to you this way, because since we already learned derivation, differentiation, I will introduce to you the formal definition of this, but first let me say this is an antiderivative. First, okay, later I will explain to you antiderivative. Okay, antiderivative. Okay, what I mean by antiderivative? Okay, when you do the differentiation of any function, okay, any function gx, okay, this is derivation, right? Then we can use that as a antiderivation. We go for gx dx, okay, and we can df, okay, x, and this is dx. Okay, the fx is basically can be explained as a new, it's not a g anymore, it's a different form, results that you may get it with a constant. Okay, this is what you've been taught most probably in the classes and in previous sessions or previous your undergrad, sorry, not undergraduate, in your what do you call matriculations or A level or whatever, even in diploma. Some of you are from Form 6. Okay, but I wanted to define this integral in a different dimension. Okay, I'm going to explain this in a different dimension. But anyway, in a simple explanation, integral, okay, integral can be defined as, is a study, of course, it's a formal definition. It's a study about what do you call antiderivative? Okay, antiderivative. Okay, antiderivative. Or in simple, you don't see this clearly, right? Antiderivative, but I try to put it that as a anti-change. That makes sense. Okay, that makes sense. Okay, what I mean by this? Okay, what I mean by this? This is something to do with the today's lesson. It's something about, okay, it's something about space, okay, or dimension. Okay, this is, oh sorry, okay, wait, okay, it's something to do with the dimension that we studied before. Okay, it's about space. We will move into the space. Anti-change means is what? Okay, what I mean by that, when I am making a change, you see, when we make a change, when we make a walk, let's say you are walking, through this space, then that can be monitored. Okay, you can monitor your progress or changes through the differentiation. Okay, I can use a differentiation and I can identify the movement of any object in the space, right? But when I say integral, we work opposite to this. Okay, inverse. It's a kind of reverse model whereby we are trying to see that anti-change. What I mean by anti-change, instead, we focus the movement, the changes of that particular object. We start looking at the space that it occupies. Okay, we will try to see how do we occupy the space. That is very important. Okay, therefore, very important way to understand integral in this case is this. Okay, in early stage, when we looking at the differentiation, I say that we look at the cause first, then we start looking at the effect, right? Okay, when you start looking, when you see, oh, okay, one object is moving, then immediately you know this is the cause of that effect. Okay, one object is progressing to the another state, therefore you can observe. Okay, you know what is the cause and you able to explain the effect. But when you see integration, when you use the integral, okay, when you're looking at the integral in this case, okay, then it works opposite to this concept. Instead, you're looking at the cause, you should able to see the effect. You should able to see the effect, and you can see later we analyze the cause of that. That means you see the effect first, then only you realize you should able to discover the cause of the effect. It means we analyze the space, and from that space you start looking for the cause. What is the cause of this effect? Okay, someone please switch off, sorry, unmute your these things please. Sorry, mute your audio please. Okay, thank you. Okay, now the next one we see, okay, therefore in this particular case the effect, okay, the effect in the space, okay, in the space which basically what I can say, the effect in the space which caused by changes, sorry, okay, I remove this, changes as cause, as a cause caused by the changes. This one I put a bracket. Okay, hello, okay, the effect in the space which by caused by changes. Okay, this is what we see as a cause will be analyzed. That means the cause will be analyzed. In this case we are trying to analyze the cause. Okay, we instead we looking at the effect, we will analyze the cause. Okay, now you see, okay, I'm moving a little bit slightly slower. Okay, but I'll try to make it one by one. Okay, the next thing here you can see is number 4. This will explain to us, okay, this will explain the space of coverage, okay, of coverage of an object, and its changes. Can I say in the space? In the space. I'm trying to just make it a layman explain. I'm giving a layman explanation here. We'll explain the space of coverage. That means the understanding here that I wanted to give you is, we are trying to see when you make a change. For example, see this object. Okay, this object moving. Okay, we actually what we are analyzing here is not about object. When the object is moved, we are trying to see how much the space, the coverage of the space of that particular object. Okay, the object can move up and down. Therefore, when you see the space also move like this, okay, we just analyze the movement of the space. The movement of that object through space. Okay, when I draw, like, you can see this drawing, right? When you start looking at this drawing, then you should be able to see, hey, there is something, some object might, moved in this space, then this is the track mark. Maybe you may say this is how I track the movement of that object. Okay, therefore you are analyzing the space. Actually, you can see that's what the first question that I did ask you. See, we go back to this. See, that means we are trying to see from here a dimension. We are analyzing the dimension. See, it's a constituent structure. Okay, the first lesson itself, I already introduced to you what is dimension, because we wanted to see the constituents of the structure of all the spaces. Actually, there is only one space, but within the spaces, we can create many spaces. Okay, we can create many spaces. Of course, some of you never agree with me. There might be several spaces. Yes, I agree with that. But what I'm trying to say, within the space, there can be we can create many subspaces. Okay, we can create many subspaces. How could this possible? This is possible through integration. That is a very interesting part. Okay, actually, integration is in a simple analysis, we may say, okay, as a conclusion, this is number 3. Oh, this is number 4. Okay, this is number 4. Number 5. Okay, number 5, that basically we may say is explain. Okay, in simple, we may say this may, okay, it's actually explain the visual effect. Actually, it's giving us visual, okay, or explaining the visual effect of changes. Okay, explain the visual effect of changes in the space. Maybe I'll try to, because I'm just creating the sentences, because in the space. Okay, this is the idea. Actually, basically, we can say it's a visual effect of changes in the space. Okay, therefore, we are trying to explain here. Okay, we are trying to explain the visual effect of the changes in the space. Whenever we try to explain the visual effect of changes in the space, then automatically you already started using integration. Okay, that means in your day-to-day life, you are explaining the visual effect, that means you are using integration without your knowledge. That's what I wanted to conclude. Okay, now let me start formally. Okay, we will go to important part. You see, it's already taken more than few. Doesn't matter, don't worry, I can cover the syllabus, I know. Okay, this is first experience to me also using this kind of tools. Okay, that's why I'm a little bit uneasy. But I think later, once you already used to, then you're able to write or I can create the things, because I like to create more effect. You see, every time I try to give a notes, then I can draw more visual. Mathematics is a visual understanding. Therefore, you need to, if you wanted to really understand mathematics, you need to understand, okay, the what you call every single aspect of mathematics through visual. Okay, now we go for number 1. This is number 2. I'll try to make it. This is number 3. Okay, I wanted to tell something about relativity and general relativity and relativity bit. Then after that, I'll move into the Rayman sum. Okay, one of the greatest contributions to this world is many of you will agree with me. And when I say who is the greatest genius, one of the greatest is one of the greatest genius in the world. Of course, everybody will agree with me. And Einstein is the greatest genius. Okay, but behind the screen, behind the scene, behind his contribution, there is one of the great men, is I may say is a pillar of the what you call the discovery of general relativity theory. Okay, no one actually able to see him unless you analyze the whole general relativity theory, okay, of Einstein. Okay, his name is called Rayman. Okay, Rayman is one of the very genius thinker, and he is the first person discovered the universe. Basically, there is a space. Within the space. There are many spaces exist. That means the multifold. He used this word, multifold spaces. Okay, therefore that means there are many folding, like what I can say is like onion. When you take it onion, then there are many layers, right? You can peel it off. Similarly, the space also is similar to that. Okay, he discovered the mathematics, okay, where you can discover many spaces within one space. You can see many subspaces. There could be a many spaces lah. Okay, I'm not going to say subspaces, but there are many spaces within the space. Okay, he is mathematics. Basically, Einstein used his mathematics. Okay, his contribution, or actually it's a multifold or manifold spaces. It's multi or many. Sometimes some people they use a manifold. Okay, spaces. That means this contribution actually helped Einstein to discover what now we call it as a general relativity theory. Okay, with that, therefore the Rayman also is one of the biggest, okay, is a fundamental contributor to the integration. Okay, therefore we're going to see his contribution to the integration. Therefore we call it that as a Rayman sum. Okay, Rayman sum is a very simple. Okay, very simple. He introduced a very simple logics to us to understand the integration. Okay, the integration. Therefore you use this fx. Okay, then he started, okay, he wanted the simple question that area under the curve, right? Okay, there is a curve, okay, and let's say there is a curve lah, okay. This is a ball. Let's say the ball moved, okay. I throw, then it moved like that. I don't know how. Don't ask me, okay, what is the physics behind this, okay, but it's fall, okay, let's say, okay, the ball back, okay. This can be a particle. You can imagine this is a particle, okay, the movement of particles. Okay, therefore, Raymond managed to introduce one simple system called he divided the space. He divided the space equally, okay, he divided the space equally, okay. Okay, equally, and he has given the kind of range maybe that could be negative, sorry, del x. Okay, we can take it at each range as a del x. Okay, basically what he did, he said all this, okay, we know this is f, right? Therefore we can calculate this as a one small rectangle. Imagine, but this is not a complete rectangle, but we can call it this is a rectangle. Okay, therefore he introduced this concept called, first wait, before I introduce this, he add up x to the del x first. I hope that you can understand this is a summation. Okay, there are I to the z, maybe 1, I take it as a and. Okay, here I expand this first. At least some of you can see this, what is going on. x1 del x Then after that, fx2, okay, del x, and etc. etc. If I add on, okay, if I add on this, okay, you can see this is some simple logics actually is using this model, okay, del x to the fx1, for example, okay, small, we are calculating the rectangle, okay, then we add on. But in simple way, he used this another concept called del x if approach to the zero. That means we are trying to make this as small as possible, as smallest as possible. Therefore, it's an infinitesimally smallest. You can you get me? Now I think you can connect and you can relate the word infinitesimally smallest, which is approach to the zero when the del x become as smallest as possible, as smallest as possible to the events. This is where you can see the time as well. You see the time is already here. Okay, we are trying to see the space. We are trying to see the space as smallest as possible with under this summation called xi to the del x. Then this automatically can be explained x. Okay, maybe I call it this as a b to the a. Therefore, it's a b to a fx dx. Actually, this part you can see the dx is a contribution of del x and the fx is a fx. We are times with that, but this is a infinitesimally smallest. Therefore, it's a integration b to the a. See, that's all. But you may say that's all now, but it's very hard to design this problem. See, it's not like it looks simple, but I think this contribution is enormous. Okay, enormous contribution. Okay, therefore let us move on. Okay, wait, is it okay? Still we got a time. Okay, now at the same time, okay, this is a Rayman sum. Okay, Rayman sum contribution. Basically, Rayman analyzed the problem of area of under the what you call any curve can be calculated using this method. What we call as a fx, the limit. Okay, he used the limit. Okay, I will go through with you the limit. This word, limit is not an easy, simple word. There are a lot of message inside here, which is later we go through in detail. Okay, but at this moment, at least you can see. Okay, I make it that del x to the infinitesimally smallest to the zero, approaching. It's actually is not yet zero, but approaching to the zero. Okay, now get back to the same guy. I will introduce to you another guy, another very intelligent contributor, but we won't learn this guy's detail, but I like him very much. Okay, this guy name is Lebesgue. Okay, integral. Okay, this guy, Lebesgue, is this guy's contribution is another enormous contribution to the integration world. Okay, functional theorem. Okay, functional theory. He introduced what we call as a functional theory, and now at this computational world, his contribution being used enormously. Okay, enormously. Okay, what he did a simple way. Okay, you may laugh. You may laugh definitely when I explain to you. You may say, wow, sir, what is this? His contribution is different. He didn't use this to the x. Okay, you see, we divided just now based on the x-axis, right? But he said, no, I don't want to use x-axis. Instead, I wanted to go for y-axis. Okay, wow, this is his contribution. He used different method. He used a y-axis. Maybe you may say, sir, this is a very simple. What is the big difference between this? Is a big deal? Yes. Okay, it's a very big deal. Okay, therefore, when you start using this, I don't want to go into detail. Okay, I don't want to go detail. Therefore, is allowing in this method actually allowing one assumption. Okay, allowing one assumption, which this is something to do with this. You get the 0. Later in the limit, okay, all the mathematician basically, until today, no one know what is the answer for this. 0 times with the infinite. Okay, what is the answer? Okay, almost all of them, they will say unknown. This is unknown. Okay, but okay, when we use a Lebesgue method, you will be able to use this assumption and you can proceed to work with this. Okay, it means in this particular case, when I use a sine x to the x, okay, sine x to the x, I can proceed to work. Okay, I can proceed to work with this. Later I will try to explain to you what is this and how do we deal with this kind of problems. Okay, now at this moment, okay, maybe you won't able to see what is the contribution of this. Okay, but later we will see how we proceed to that. Okay, again, this is another contribution. Okay, so far it's okay. Now let us move to very important area. Okay, now I ask this question. Can you quickly answer to me? B to the A 0 dx. What is the answer? Can you? I think almost all of you are quiet. Okay, some of you say 0, some of you say C, constant, etc., etc. Okay. Okay. The answer is 0. Okay, it's not constant. Huh? Answer is 0 because it's definite integral. Okay, it's definite integral. Okay. Another question is, what is the answer for this? Oh, quickly respond. Okay, the answer for this is C. Very interesting. This is opened. This is a definite integral. This is a open, right? We call this is a indefinite. Okay, indefinite. Okay, indefinite integral. Question here, why? Okay, why for this we get 0 and indefinite we get C? Okay, why? My question is why? Okay, can you explain with the logics that I explained to you just now? B minus A. Because of the B minus A, yeah, but A, please remember, this is B minus A is not a 0, of course. But why? Why for the indefinite it become a 0? Can you? Okay, I'll try to give you one idea. Okay, I'll give you some idea. At least you can see something constant. Okay, something is constant here. In what? In the world of visual effect. Why? Why something is constant? Okay, in this case, we are saying something is constant. It's in constant. Okay, in the world of visual effect. Why? Okay. Okay. I use a definition, but this can be only proved. Okay, we can prove this. Okay, if you want the proof, you need to use Lebesgue method. Okay, I don't want to go into detail, but in a simple, generally you can see that it's a d0 plus c, okay, with the dx equals to 0. We use the antiderivative here, okay, antiderivative. At least we can prove opposite. We can we can explain this by now you can see plus c, then we can get dx. At least we can say this. Okay, I will give you the explanation later. Okay, when I proceed to advance this stages, I will give you the explanation why C, we are getting C. If in between, if anybody able to discover, you can share that with us. Okay, you can share with us. Okay, after the session, maybe if you got some other time, then you can we can share the sessions. Okay, we have done. Okay, up to here, I already explained to you what suppose you need to know for the integration theoretically. Okay, now onwards, we will go for methods. Okay, these methods will be very aggressive. Okay, what I mean by aggressive here, okay, you need to know exactly, okay, when people ask you what you understood, what you understood with the integral, by now you should be able to say, hey, integral is an anti-change. Whenever I see the changes, then I'm doing differentiation. Whenever I perform integral, it means I'm trying to analyze the space. Okay, that means I want you to have some kind of beautiful explanation to explain the integration. Not I don't want you all to explain by using what you call mathematical technical explanation. Let's say your brother, okay, 5 years old or maybe 6 years old. Oh, okay, maybe standard 1 or standard 2. He asking, sir, brother, what are you learning? Yeah, you may say, okay, now my lecturer is basically teaching us integral. Okay, explain to me what you understood with that word integral. Then you cannot say integral is a graph under what you call a curve, and this is very technical. You're all very too small to understand all these things, and etc. etc. That means you are making him scared. Okay, then he will laugh at you. Hey, you don't understand actually what is integral. Basically if you can understand the integral, you can able to explain to any level. I am saying any level, even to the kids, to say this is integration. Okay, this is differentiation. See, you can able to demonstrate to them and show to them, okay, this is what I want. You don't simply learn something but you can't explain that. Okay, but you can technically explain, but technically you can score A, but the end you don't know what it is. Okay, and how people are actually using in the day-to-day life. Therefore, if you cannot connect, then impossible for you to really enjoy or appreciate that all this kind of learning. Okay, therefore, okay, after this I will go into detail, because okay, into the methods. Okay, we will study the methods. Okay, there are solidly I will introduce to you. Okay, I want all these methods in your mind. Okay, when I say, okay, what are the integration method, how many methods are there, you should be able to explain to me. Minimum you should be able to tell me there are, beside general properties and rules, there are 8 rules. I want you all to master the 8 skills. Okay, I'm going to introduce to you 8 skills. Okay, that means in any circumstances, once you're able to use these 8 skills, definitely you should be able to solve the problem. But it's not easy. Okay, it's not easy. The method that you already learned before, I'm going to introduce to you something slightly different. Okay, slightly different approach. But the first one, this is general properties and rules. Therefore, this is very important. First one, this is a fundamental. Therefore, we go for the general properties. Okay, we will learn general properties and rules. Okay, we don't have time. Okay, we don't have time. I think you all need to rush back to your other classes. Therefore, I will introduce next sessions quickly, but I wanted to write, you also follow. But there is, I already taken extracted all the information is here already. You see, I already put all this method is here already. But don't worry, okay, it's all in from my notes. Okay, but I want you all to write. Okay, when you write, follow my, this thing, you can correct me. You can say, sir, this is supposed to be like that, or this is how it works. At least you can understand. You can understand the mathematics. You can follow me. Not only follow, but you can actually practice. Okay, this is a kind of practice basically. then you should able to, okay, put it into very nicely, you know, whenever people ask you what is integration, okay, integration is this, and there are 8 methods, and how, you know, 8 methods works, and etc, etc. I want at the end of the semester, you should not only you should able to, you know, you may get A or whatever, okay, but you should able to explain, you should able to use, okay, it's not simply what I call, you know, you learn and score A, and later people ask you what you learn. I forgot already lah. It's all, don't ask me now. Okay. I won't. I don't want that kind of these things. Okay. Anyway, thank you very much. We will meet in next sessions. Okay. Next week. On Wednesday, there is a quiz. Huh? I hope that all of you are able to attend to the quiz and try only 5 questions. Only 5 questions only. Have a look on that. Okay, 5 questions and give a try. Whatever level, but it's whatever that I already cover. I already cover all the things, you know, with you. It's within the chapter that I cover, differentiation only, nothing else. Okay, differentiation only. Okay, 5 questions, quiz. Try to attend. Okay. Thank you very much. Bye. If you have a question, you can ask me after the sessions. Okay. Thank you very much.